I don't know, maybe this is a real talk and I should be nervous, but I'm, you know, you're in your house. How much more comfortable could it be? What I'm going to discuss today, I first presented at Ken Witherly's DMEC workshop at the PDAC this year. That was titled The Value Proposition for Geophysics. It's not just discovery. And that was based on a discussion he had, or an outcome of discussion he had with a guy called Richard Shoddy, who is an Australian who collects a lot of exploration data, exploration spend and discovery rates. He tracks all this stuff. I'm not going to talk about anything that he did, other than to say that in one of his talks, he kind of slagged geophysics as being unimportant in discovery. So Ken got his bee in the bonnet, and you know, he did the right thing. He talked to Richard, and he got Richard to come to the PDAC, or he found out that Richard was coming to the PDAC, and he held this DMEC workshop. And then in that, he invited a bunch of people to talk about different aspects of geophysics. So I decided that I would talk about inversion. What I'm going to talk about today is not about discovery. And in terms of a value proposition, if I've added anything of value, or if I say anything of value, you can tell me that at the end. But what I am going to talk about is a retrospective trip through my 25 years as a geophysicist, which began, my first job with Kennecott in 1996 was just as the first inversion software, I think, was being rolled off the line at UBC, kind of DCIP and Mag3D. And that software was at the time available to general practitioners. And I say that because specialists, inversion specialists, certainly didn't exist then. I know in my formal education, I never had any courses on inversion. So I had to figure a lot of this stuff out as I went. And fortunately, I had a lot of smart people to talk to, and people from UBC. I guess the other thing about the non-specialists, I say that with my tongue in my cheek, because the one thing about the geophysicists at that time, and not that I was one of them because I'm just starting, but you could show them a profile of basically any kind of data, and they could probably make a pretty decent interpretation right off the bat. So someone who could actually look at an IP pseudo section and tell you, see through the pant leg and tell you where to drill, as opposed to today, where I think that skill is lost, and we basically have to invert the data. Anyway, my talk today is entitled From Smooth Models to Pseudo-Geology, and those first models that coming off 25 years ago, they were all smooth models. They produced blobs, they were L2 norms. We're going to talk about these things. And they were good, but we basically spent the next 20 years trying to get rid of them. So this is the outline of my talk. I've basically just given the introduction. So I'm going to continue. We're going to talk about the inversion hype cycle, which was, well, I've called it the inversion hype cycle, but I've basically ripped it off from the Gartner hype cycle, which is about technologies. We're going to talk about that, a little bit about inversion basics and pitfalls. And I have to be careful what I say, but the inversion basics are going to be pretty basic. I have to be careful about what I say because of some of the people on this call. And then towards pseudo-geology. And in getting there, I think what we need is data, not just any kind of data. We need multi-parameter data sets, which some companies are happy to collect and others are still loath, or it's difficult. We need petrophysics. I think we've always had petrophysics, but what we require needs to be statistically relevant and more than just a few numbers from a few hand samples. And we need to learn how to use constraints. And the constraints isn't just the petrophysics, but we need to be able to apply geological boundaries and structures. And I think some of the original GIF inversion tools had mechanisms to do that, but you really had to know how to program. It was very difficult. There was no convenient front end to do these, and it's still a work in progress. Then I'm going to talk about the TLIKWI diamond deposit up in the Northwest Territories. I'm going to spend some more time about the plateau of productivity. You're going to learn about that. And then at the end, we're going to, you're going to see why I've included the cast of Ratatouille. It's one of it's probably my favorite animated movie ever, almost. So if anyone can can think about it, you should write it down. So before I get into any of this, I'm going to talk about the project management tire swing. And I'm not sure if anyone on this call has seen this before, but I'm basically going to start in the end. In the bottom right corner is this box. It says it's a tire hanging from the branch of a tree. It says what the customer really needed. And I think that what our customers really need today is pseudo-geology. They need an inversion that is informing them not just about where the rocks might be magnetic, but about the rocks themselves, which rocks are resistive and which rocks are conductive. And as we learn to overlap these things, we're going to be able to map geology. So this is what we want. The other 9 boxes on this, basically, to me, they all correspond to this, well, this smooth blob that we have in the top right. We just have this susceptibility blob. And the thing with the management tree swing is that there are multiple interpretations to a fairly simple problem statement. So again, what the customer wanted was a tire hanging from a branch. You know, if we go through these, and I like doing this because I think it's funny, but in the top left, you know, how the customer explained it. So often our customer, they can't often exactly tell us what they want. We need to figure it out. So, you know, is it 3 planks? How the project leader understood it, right? He didn't bother to cut the tree, how the analyst designed it, you know, how the programmer wrote it. This is one of my favorites, how the business consultant described it. And I think this is going to be part of this is going to come up in the inversion hype cycle. You know, how the project was documented. I think we can all relate to that. What operations installed. Oh, this is a great one for you consultants out there, how the customer was billed, right? There's a roller coaster, all we want is a tire swing. How it was supported, that's pretty close to how it was documented. And again, what we really wanted. So keep this in mind. And we're going to talk about the inversion hype cycle, which, like I said, is ripped off from the Gartner hype cycle for technology. And what this starts off with is a technology trigger. And the axes are visibility on the Y and time on the X. So we have low visibility at 0 time. Something triggers a technology. In this case, you know, a bunch of chief geophysicists at the time, Jules, Peter Kowalczyk, Misak Navigian, and others, and I'm sorry if I missed them all, decided with Doug Oldenburg that you know, inversion would be worthy to spend some money, invest some money on inversion. So there's this technology trigger. In the next 5 or 6 years, and these are my takes on the dates, and we can argue and move them forward and back, but it's not really important. At least I don't think it's important. About 6 or 10 years later, we came to the peak. I think at one point, we were selling inversions as a panacea. This is going to be the next smoking gun, and everyone wanted them done. They wanted them done now. And there were some successes, and we're going to talk about one of them. But after a while, I think the outcomes of these inversions didn't lead up to the hype. They didn't drive the next stage of tier 1 discoveries. And for good or bad, I mean, that's what happened. So then after the peak of inflated expectations, things fall off, and you enter the trough of disillusionment. Just so happens that that was the time of, well, everything was booming in the world, and then we went into the global financial crisis and budgets tanked. But I remember around that time trying to sell some surveys to my general manager at Tech, a mag survey, and the answer was, well, all you're going to do is plot up a bunch of maps and draw some circles on it. And my answer at the time was, well, the only reason why we do that is because you only give me time to do that. Like, we need to have time to make these interpretations and these value-added products that you want. And we need to budget that into the time. And that started a huge discussion that was very fruitful, I felt, such that about 3 or 4 years later, I think we were beginning on the slope of enlightenment. We were starting to educate managers into what we could do, trying to have them give us not just the software. It's almost like you give your child allowance and think that's enough to be a parent. No, you have to give them time and the opportunity to grow and to fail. And I think we've been doing that. And we were doing that certainly in the last decade. And I think now we're riding this corner. We're on what is going to be the plateau of productivity. At least this is what I'm arguing. So the technology trigger, I think, was this thing called the Joint and Cooperative or JACI Research Consortium at UBC, and this was Doug's first consortium. And look, it's a great name, the Joint and Cooperative Inversion of Geophysical and Geological Data. It was a great name, but the thing is, it didn't even come close to doing that. I don't think there was anything joint and or cooperative about the first inversions that we were doing. But still, it got things off the ground. There was 2D DC IP and resistivity surveys, 3D mag, 3D gravity, and 1D EM. And those were the sponsors. So BHP, CRA, Caminco, Joules, Falconbridge, 20 watts, Hud Bay, Inco, Alan King, Joe Inman from Kennecott. Anyway, the list goes down. So those companies got together and they started off, I think, this journey that we've been on ever since. So the peak of inflated expectations came, and again, there were a bunch of neat successes. This is one that Theo Aravanis, for those of you who know him, worked on directly. This is the Century Zinc Lead deposit in northern Queensland, in Australia. As it turns out, and Theo would love to lament what happened, he was running a survey that came to some river or something, or it started to rain and they were ordered out and they weren't allowed to do the next line or extend the line. And that line extension would have come up with this. In the meantime, they didn't do the extension, but they went and drilled it anyway. So the drillers found this first, but this is Century. This is a wonderful result. I think it's really obvious to see what's going on in here. And it ended up being a mine. And this, I think, was held as one of the prime examples. This is what inversion could do. This was a great case. I think the physical properties lined up perfectly. And of course, it's always great if you can collect data over what turns out to be an economic deposit. So with that in mind, I'm going to step back a bit and we're going to go into inversion basics. And when I gave this talk, and I forgive you if this is too basic, but I was in the original DMAC presentation, this was I thought the audience was going to be more geologists than geophysicists, but even when I was putting this together, I thought this is a great refresher. So we have the simple 4-parameter problem here. We have 2 equations. There are 4 unknowns and 2 values. And what we're trying to do in inversion is we're trying to solve these 2 simultaneous equations. And in the absence of other information, this is really, really difficult to do. So here we have 4 models and they all fit the data. So often, I mean, if you believe Occam's razor, the simplest one, right? If you don't have any other information, the simplest solution is the best. So that might just be model A, where we can just have 2 for each of them. We have model B, model C, model D. And again, they all meet the data, but because they all fit, how do we choose which is the best one? And I think this is where the question gets interesting, because we have to decide what the question is. So we can do an L2 norm and sort of call this the flattest model. So that would be the first one. When we add all those numbers up, in this top one, where we take the difference between every data point and the next data point and square that, we get 0. So if we're looking for a flattest model, or the simplest model, that's going to be A. If we can define a different norm, which is the second column, and that can be the smallest model, so that's the smallest number of all those. Or we can have, so that's your L2 norm, sorry. And then on the other one, on the first column, we have our L1 norm, and the smallest there is model D. So we have 3 different options to choose from. And they all fit the data. And And this is the problem that we have as geophysicists every day. And this is the problem that we need to convey to geologists. They don't have to really understand the nitty-gritties, but they need to understand that there are multiple solutions to each of these problems, and we need their help to choose why. And this is where the constraints are going to come in. So what about the data side? Data are inaccurate, and we know from I think it's George Box who said, all models are wrong, some models are useful. So any model that reproduces the data is guaranteed to be wrong. And what we want to do is find models whose predicted data are consistent with the observational errors. We use chi-squared statistics. And the expectation is that phi d, at least in the way it's defined in UBC, phi d equals n, the number of data. And this is the key bit, I think, to me, with a standard deviation of the square root of 2 times n. So that means that there's a 66% chance that the misfit between the true model and the observation will lie in that range. So even if we convey that to geologists, say, look, yes, this fits, and it fits really well, but we're still trying to fit this broad distribution, and things float around that distribution quite easily, as it turns out, because that's 66% chance is pretty large. So let me get into the trough of disillusionment, and I think we probably all have examples of inversions gone awry. This is one that I had something to, well, I had a very side thing to do with this. This happened, I think, from Turkey. This is some data that was collected. And here we have actually and I just always show my 2D inversions like this. On the top, we have the observed data. And in the middle panel, we have the inverted chargeability. And then on the bottom, we have the inversion, because I always like to show people that indeed my model could reproduce the data. And we show this to the geologist, and they go, okay, it reproduces the data, fine, but the geology just looked complicated. It doesn't look good. So it raised some spider senses. Anyway, we then went and started to QC the data. It turns out, so those 2 points there that I've just highlighted, they are really wanky points. And it turns out that if you remove those 2 points from the data and reinvert it, changing nothing else other than removing those 2 data, the answer looks like this. And this is what's weird with the online thing, because I can't hear what you guys are saying. Ooh, but this is what it looks like. So we've gone from inversion that looks like this, which was kind of geological nonsense, to this, which actually did make sense.
Whoa, it's so good. There you go, you got it.
Great, thank you. So we were lucky because we had some reasonably sophisticated geologists who questioned what we were doing and said, look, like this doesn't make any sense at all. But we don't always get that. And I don't think it would be difficult to think about that. There might be a case where someone just takes this and goes, oh, great, and thinks that there's some drill target here on the left at at 200 meters deep or whatever when it's not there. So this is my trough of disillusionment. I think we started to have people who would do inversions and not really know what they were doing. In this case, it's not that we didn't know what we were doing. The first one was, well, yeah, I mean, inversion was done without a proper quality control. And just because you have someone who knows what buttons to push, they still need to have some insight into the data, how it was collected, what it means, and what makes sense. And this is actually a talk I gave at the PDAC in 2016. So let me get on to the slope of enlightenment. And to me, the slope of enlightenment really came when I first read or saw a presentation from Nick Williams, who got his PhD from UBC in 2009. And I think most of you know that, at least by training, initially Nick was a geologist. So he was a geologist who went into UBC, and I think that did a lot for the group. It kind of dragged them a bit into reality, and maybe his PhD was a little less theoretical than than the rest, but I think it's one of the most useful that we've ever had. So this, I believe, is from chapter 2, where he did this forward modeling study. And he starts off with a true density model that you can see there, and then he did he forward modeled that, and then he did an inversion. So this is just the recovered, the unconstrained, just the straight L2 norm of that density model. So we're just going to come down. Then he went and he added surface constraints, so basically a geology map, and he reran the inversion, and it looked like that. Then he added something about the basement. He added some basement information in there. And then he added a borehole. And then he added 2 boreholes. So in each one of these, except the first one, he's basically adding constraints, adding surface constraints, basement geometry, and then borehole data. And I really like this because it shows that the biggest bang for the buck, the biggest step change is in the surface constraints. I think borehole constraints are kind of sexy. When Voxy first came out, one of the first things they added was borehole constraints. But if you think about it, you can have a model that has a couple of 100,000 cells. A typical borehole might touch 20 of them. So you're trying to impact a model with 500,000 cells by putting constraints on 20 of these. Whereas your surface geology, that may actually touch 10,000 cells on surface. And if you could do anything about predicting depth, you could actually push that surface geology down. Even if you only pushed it down 50 meters, you're now impacting 30,000 cells, 50,000 cells. And those cells are closest to the sensor, so they make a huge difference. And when I read this and saw this, it really struck me. And I've been trying to get our geologists to work with the geophysicists so that we can do surface constraints on all of our potential field models. And it's still a work in progress. I will say, so I'm going to just talk a bit more about this. When I was in Australia, I was talking to a geologist once. He handed over some data, and he said we need a mag inversion. And I went through this talk. I said, well, do you have any constraints? He said no. I said, really? I said, you don't have any maps? And he said, well, we just have these government maps, but they're 1 to 250,000 scale or whatever, and they're wrong. Like, this isn't a granodiorite. It's a diorite. It's not a granodiorite. And I'm kind of saying, well, look, that's fine. What's this yellow stuff on the map? He said, that's cover. I said, oh, well, is that mapped right? He said, oh yeah, that's right. So right away we knew where there was cover, and we knew where there was outcrop. And then I said, are there any drill holes? And he said, no one's ever drilled this. I said, but looks like there are some farms around here. Are there any wells? Oh yeah, we have the well database. So is there any information in the well database? He says, well, none of those holes actually reach bedrock. I said, well, actually, but they do tell us how deep bedrock isn't, or it does put a minimum depth on bedrock. So we were able to make a forward model where I could throw in non-magnetic, essentially non-magnetic or non-susceptible cover rocks down to a decent depth, and it really helped. So that's my little story about that. So more into the slope of enlightenment, I think UBC has been doing a lot in the past number of years, trying to push different kinds of model norms. And I talked about these before. The small was just that was column 2. The flat was column 3. And then there's a small versus a reference model, and small and flat versus a reference model. And there's going to be variations of L1 and L2. And there's some very good work that's been done in some online applications where you can fiddle around through these things. But I think one of the keys is when we run an inversion, we need to be running multiple inversions changing as many things as we can. So running different norms and then sitting down with the geologist and having a discussion about which are the ones that look most reasonable. On to petrophysics, this is something I pilfered from a slide from Doug, but I think this is hopefully pretty known to most of us, right? The geologist is talking about texture, lithology, and stratigraphy. We're talking about density, magnetic susceptibility, and conductivity. And, you know, in the end, that we can fingerprint these. A lot of rocks can be fingerprinted petrophysically. I also think it's good because geologists often like to, you know, there are lumpers and splitters, and there will be splitters who will separate two different granodiorites, the, you know, the feldspar-rich granodiorite and the whatever. But in the end, it has the same susceptibility. So as geophysicists, we lump them all together. And I think having these two interpretations of the, or these two views of the same thing make for some very interesting and productive discussions. So on the petrophysics side, basically, this is where I mentioned before that we need multiple parameters. If we really want to do pseudo-geology, we can't just have mag. We need mag and gravity and conductivity for starters. So, but at least two. And here, this is what we can do when we get those measurements, and we get enough of them to be statistically meaningful. So this is not someone taking the meter and making 10 hands, you know, 10 mag sus measurements on 10 different rocks. We really don't understand what's going on. So this is why borehole data, I think, is great, because we actually get enough data to be statistically meaningful. But when we get those data, we can start to make diagrams like this, at least in terms of the table and these histograms on the side. So this plateau of productivity in, I think it's probably about 2017. I was in Perth. I got invited to go to the University of Western Australia, and I sat in some talks. One of them was from this grad student, Jeremy Giroux, who graduated in 2018, and he was actually one of the first people I saw who was really focusing on petrophysics and how we can throw those data into our models. Now, I'm not 100% you know, up to all the technical details of what he did, but so I'm going to distill it down into something that at least makes sense to me. He basically did the same kind of L2 norm that UBC does, but he was throwing in, he basically just extended he put more terms in the functional equation so that he had a term for the petrophysics as well. And he also threw in some Monte Carlo uncertainty, and you can tell because I'm kind of stammering that I really don't 100% know what I'm talking about. But he did all this, and he came out with these models. And there's what he started with. And he basically could run these probabilistic inversions. And here he's come out with outputs that are focusing on these different lithologies. So he was able to recover basically all the lithologies, and he was able to recover them very, very well. So this was, to me, this was something that said, hey, we're on the right path generally. Whether this probabilistic version is the way to go, I mean, he was working more in sedimentary environments. Was it going to work in a porphyry environment or a hard rock environment? To me, that was less important than this is the kind of work that we need to start to look at in more detail. So after that, then I met Thibaut, or I was at one of the UBC meetings, and I met Thibaut, and Thibaut, in my mind, was doing, at least the end goal was similar to what Jeremy was doing. He was throwing in, he had a geological model. He was throwing in petrophysics and the geophysical inversion. Now, rather than throw all these things into the same functional and come up with one minimizing term that Jeremy did, Thibaut actually splits them up and he kind of iterates between them. And Thibaut's on the call, so he can tell you everything that I've said that's wrong at the end of this. But basically, you do a geophysical inversion, you do a petrophysical inversion, you do a geological inversion, and you start to cycle through these until we come up with a model. So he's published a paper in JGI that everyone can download, and I guess we're actively, I'm hopefully waiting his PhD and access to some of these new tools in the GIF software. So on the plateau productivity, this is from the TLIKWI kimberlite, and the next slide is going to show a few more things. But in the classic inversion, the smooth result on the left, we have this Gaussian-like distribution, and there the distributions are in the histograms, and the black dots are basically the susceptibilities that came from the model. And we basically see that in the smooth model, most of it was skewed towards zero susceptibility, which is kind of the country rock, and country rock density. But this isn't really, when you're looking for kimberlite, sorry if I didn't say that before, this isn't optimal. I mean, I think if you want pseudo-geology, you want to learn a bit more. So with Thibault's inversion methodology, you're actually able to break these things out so that we have data that susceptibilities, inverted susceptibilities that cluster around. This is the pyroclastic kimberlite and the volcaniclastic kimberlite, and they are separated from a higher susceptibility hypabyssal kimberlite. And then we still have the background rocks here in the corner. So I think if you can start to construct a model like this and show that to the geologist, we start to have some very interesting discussions and some very interesting engagement that I think will be successful for both parties. So this is actually work that I did because I was with Kennecott, and I did a Northwest Mining Association paper on TLIKWI. So these are the three inversions that I did. I did a density inversion, a mag-sus inversion, and a conductivity inversion. These are probably like 100-meter cells, and they were all huge. And you can see I had three kind of blobby targets. The conductivity is just showing the top, and we now know that's not true. These things are basically conductive all the way down, but the helicopter systems were, and the inversions that we had would only show the top. And it was good at the time, but I think, again, is this what the kimberlites really look like? No. So this is Thibault when he had his gravity petroinversion done on its own, and there's a mag in the top right. We showed that histogram, and then in the bottom is the geomodel in the bottom right, the geomodel post-inversion clustering with 6 clusters. Okay, so in fact, so this is individual inversions whose results are clustered after the fact. And this is the result when you actually throw all the data in together in that algorithm of iterating through optimizing the petrophysics to meet the Gaussian model, the geology, and the geophysics. And now we start to get something that is very clustered and very compact, which is something that we want. It's probably better than an L1 norm, which is compact, but often doesn't show us what we want. So we're basically coming to the end of the talk. How do we stay productive? I've got this vicious cycle in Einstein's definition of insanity. We have to stop doing what we've always been doing and embrace some of these new methods that are coming out. I think we have to consider the value of information proposition, which is something that we almost have to do at times in Anglo American, but we have to say, if you give me this $1 million to fly this survey, it will provide this much value back. And we actually take some time to think and say, you know, we think even if we say, look, we think it's going to help you drill 5 less holes. It's going to help you drill, right? Even if if you go negative and use it as a condemnation tool, we are going to drop ground much more quickly because we are going to be able to determine not to focus our resources. We are going to drill less holes. And in collecting this data, not you might find a deposit, it's going to save you more than $1 million in wasted exploration costs. So that's the geophysics as a condemnation tool. What I think is required is multiple high quality survey data collected at the right resolution. We need geological constraints, and I'd say at a minimum, surface geology. I think unconstrained, at a minimum, potential field inversions, they just need to stop. We need statistically significant petrophysical data, and we need trained practitioners, which is why, I don't know if any of you included, why I included the cast of Ratatouille, because anyone can invert doesn't mean everyone should invert. And with that, I'll just acknowledge people who have helped along the way. UBC-GIF, these are numerous people who I've had very extensive and enlightening discussions with over the years, from UBC, Jeremy from UWA, and the cast of Ratatouille. So that's it.
Excellent talk. Thank you, Joel. This is excellent. You went through so many important points. That's really good. We're gonna have a question session for everyone. If you want to just type your question in the chat box, or you can also unmute yourself. I see that Sergio is ready to fire up here. Maybe I have one. I'll start with one just to prime the audience. So I'm curious because you have to deal with upper management, you know, like people who are not geophysicists that are deciding on budgets and everything. And you were saying earlier that at Tecominco you had a hard time, right, during that low dip of 2008 or whatnot. What's your feeling now? Do you find it easier to sell geophysical survey and like interpretation cost to upper management?
Look, there are still budget constraints that we have to live in, but when I propose doing a survey these days, I spend a lot less time arguing about the value that or the base value that we get out of it, and I don't think I need to argue to have time put in for someone's inversion. Right, it's now understood if we do a survey, we are going to budget whatever, a month or 6 weeks of someone's time to run the inversions after. So we don't have to argue for that anymore. Still have to argue why this option, right, the geophysics option is better than collecting more geochemistry or something, right? So those are still arguments that we have. We still arguing about resolution. And the resolution arguments are actually kind of great, but they're discussions about what to expect. Okay, if you won't let me fly 100-meter lines and we only have 500-meter lines, this is, you will know that this is what you will not get. And then we have a discussion. Sometimes we settle on 250, and sometimes we settle on 500, and sometimes we win and we settle on 100. But I think those are the good discussions, right? We're not arguing about the basic value of doing this work anymore.
That's good. And kind of a segue, we have a question from Richard Smell. He's basically, you can probably read the question in the chat box, but his question is that the borehole, collecting borehole petrophysics is obviously very expensive for companies. And you probably have to justify it to management to do it. Do you think, can you come to mind any like case histories that were really like important, to showcase the use of borehole geophysics?
The one thing I've learned working for Anglo American is I think that we in North America are probably on the trailing end of borehole geophysics. So the South Africans have been doing borehole petrophysics for a long time. They do it quite well, and they've been doing it routinely. So I can think of, off the top of my head, probably 5 different borehole geophysical service providers in South Africa, right? All based in and around Johannesburg, and it's helped that they've had coal and iron ore and platinum, all within and diamonds, all within a day or two drive. I think in Canada at Tech, the way I got around this cost was I just bought my own system. So, because we wouldn't do it, of course, yes, because you're doing something in the middle of nowhere, and the holes might not stay open, and you're not gonna. It takes 3 weeks to drill a hole. You're not gonna bring in a contractor like in and out. So we bought our own system, and we trained some technicians to do the work, who they might have been core loggers or geophysical technicians, but they would spend their days geoteching core, going in the field, and every 2 weeks when a hole came available, the equipment was there. So that's how we solved it there. I guess Brendan can tell you how well that's still working or not.
Joe, first of all, it was a really nice talk, and thanks for all the shout outs to all the great people from UBC. Your comment about purchasing something and actually taking it to a site, can you follow up a little on that as to what they're actually measuring, and and what sort of costs you're up against, and what kind of logistics you have, and a little bit more insight about that whole process?
Oh, on the borehole side, sure. So you can probably buy a system from a company like Mount Sopris, MagSus, natural, maybe spectral gamma these days, resistivity. You could probably get that on a 500-meter wire line for I guess 100,000 Canadian maybe. If you want a televiewer, they're about another 30,000, but still, so you probably have to invest about 100,000, and you'll get a system that will get most of those, most of the parameters that you want. And then basically, once I had permission to purchase it, I kind of throw the accounting depreciation out the window and say, well, now we have it, now we have to use it. So we took it up to Red Dog, and which is a place where we had never done geophysics or real petrophysics. And I know that Boris is on the call, but when I was up there with that system, we were actually able to do every single hole that we were drilling, which shows the value of it, right?
Have those data been kind of incorporated into an inversion so that you could see its benefit?
I'm probably going to say no. And basically because, well, why? Basically, Red Dog is a big sedimentary basin, lots of shales. So the good data sets that we have is mag, and most of those rocks down to a couple of thousand feet are non-magnetic. Then we have lots of gravity data, but of course we weren't collecting density from those holes, so that didn't really help there. And what we were using them for a lot after we did the petrophysics, well, look, we collected the data. One of the best uses of it was honestly the televiewer, which fed into the structural geology, because it's such a complicated terrain up there with the folding and the faulting. It was really important to know what the rocks were doing, because we weren't drilling oriented core, so we needed to know where to drill next. And then, so that was basically it. What we really wanted was the televiewer, but we were collecting the other stuff.
Okay.
Excellent. Anyone else would like to ask Joel a question? There's many of us here, almost. We're 69, good number. Anyone else?
Yeah, Dominique, I don't have a question, but I just have a comment. Joel mentioned at the beginning that many skills are lost. And something I've noticed, especially with younger geoscientists, is they believe that the computer is going to solve the problem. So they have forgotten to learn the very basic, whether in physics or in geology. And I think that's a huge problem. Because even if you have the best computer of the world, the best AI system, if you don't understand what your dealing with, you will not be able to solve anything. Doc is in the audience. Maybe he has some comments. And Craig Hart, I hope he still is in the audience. How can we solve that problem? How can we go back to the basics, which are a lot of time very needed?
Feel free to unmute Craig or Doug, or yeah, anybody can pitch in.
Yeah, I mean, that's sort of like a perennial, ongoing problem. But I think it's something that, you know, we're trying to address, especially as we sort of move towards an open source environment where people can, you know, interact with colleagues and get, you know, assessment about, you know, what they're doing. Joel, your examples earlier, I mean, we've seen for decades now, in the sense of, you know, people have got a code, and you know, they can put some input in, and they can push a button, and they can get some output, but they don't really know, or have forgotten, you know, what the steps are to really understand what you're putting in and how to do quality control and critique your results. So it's perennially an ongoing process, but I think, you know, we're always just trying to put more information out there, more examples to show how things can be run properly, what happens when they fail. And then it's just in, you know, getting good people out there who can then really make a difference. So expand the tree of, you know, really high quality people who know what they're doing and have integrity in their processing and their interpretation. And show examples of success, and quality generally wins. So I think we just kind of pursue that course.
That's, you know, I think that's absolutely true. This you know, the open source, having good people have better access to what's out there. But I will go back to my anyone, you know, that anyone can avert doesn't mean that everyone should. I remember when Ian McLeod was first touting Voxy. I remember he told me once, he said, you know, I want to have Voxy on the desk of every geologist. And then I said, well, then, you know, I compared it to giving a child an Uzi, because they're just going to go and just blast everything to, you know, to pieces. We do need trained people who understand the data and understand, at least to some extent, the math of what's going on in these things, and are able to sort out, you know, what's a good inversion and what's not a good inversion, like that IP, the chargeability inversion I showed from Turkey. I mean, it's amazing how 2 data points on the edge, and maybe it's because those 2 lousy data points were on the edge, so they had no support. I think if you have a lousy data point in the middle of your inversion, in the middle of your data set, it has lots of support around, and the inversion can kind of smooth through it. But if you have an outlier on the edge of it, on the very edge of a data, I mean, it basically, the effects of those 2 bad points penetrated all the way into the middle of the inversion. You know, that was a big eye opener.
Yeah, and it's not necessarily just these 2 points, but because they're so wrong, you're pushing hard on all the points, right, to be able to fit them, and then you're going into some like really weird space. Yeah. Anyone else would like to say something?
Actually, if someone else wants to write a question, I'll finish answering Richard Smith. Yeah, so look, I really don't think that we should have to justify borehole petrophysics costs. Sorry, before I didn't have the Zoom chat open, I do now. Because I think if you go drill a hole that costs a couple of $100,000, and I had this argument like so often, it's like, you want $10,000 to drill a hole, and they say, oh, we're over budget. Can't, there's no more money left. It's like, well, your hole is double over budget. So you've gone to spend $500,000, and now you won't spend another 10. So it's this value of information. I think we have to be able to go in, and maybe that's the whole thing of the case studies. Do I have any really good ones that I can share like readily? No, but I know that in Anglo there are some great stories of you know, of borehole geophysics. One using televiewers and radar help them move the shaft of a mine, which ended up, I mean, had they put the shaft where they wanted before they did the survey, it would have been a complete disaster, and it saved them, you know, $50, $100 million. So it's in a company like Anglo, it's not difficult to, when you bring up stories like that, it's not difficult to get money to do it. Now, we still don't always do it. It's still a discussion, but we are pretty far along.
So we have another question from Sean. He's asking if you ever used airborne gamma to constrain your inversion.
No, but I mean, I guess you could use it to, yeah, to at least come up with domains, right, and draw domains. I guess maybe the reason why I haven't is we do a lot of work in covered areas, and the gamma hasn't always, at least where I've worked, the gamma doesn't really show a lot. But that's a good idea if you have it.
Part of your surface constraint. You've always been a big proponent of surface constraints, so there we go.
Yeah. Well, again, I mean, I think those cells, I mean, there's just so many of them, and it's simple.
Fair point for sure. So we're 7 minutes out. It just depends if you guys want to keep chatting, or we're not really restricted. The service is.
Do we turn to a pumpkin at 5:30?
Yeah, I can unmute everyone, and it's going to be a big chaos. Everybody's quiet.
Everyone wants a beer.
Yeah, I mean it's 5:30. It's a good time for this. So I guess let's close it. Let's close it there, Joel. Thank you very much for your time. It's amazing. We will put the video, because since you've agreed, we'll put it on YouTube after the talk, and then share the link with everyone.
Good. My screen says that my internet connection is unstable.
We have Richard Smith applauding.
Thanks, Joel. Okay, thanks, Joel. Really enjoyed it.
Joel.
Yes, thanks, everyone. I'll have to say it's weird talking to a screen and not getting any feedback, but you've been a great audience. Thank you.
We'll work on it. We're gonna have a catered audience for the next speaker. Only 3. They'll be nodding. Okay, bye, Joel.
Bye.
Okay.
Thanks, Joe.